All right, here we go, guys. I am going to just get right into this. This is Separate Ancestry Moments 2, Eve Consensus Sequence. So I am going to be covering some important information here in this next video on separate ancestry moments. Now, that is not to be confused with the series that I'm also doing titled The Case for Separate Ancestry. And so what I'm doing is these shorter moments in terms of the evidence for separate ancestry and the evidence against universal common ancestry. And so they are shorter and more to the point. With the case for separate ancestry episodes, I've released one so far, and it was about an hour and 40 minutes. And so those episodes are more comprehensive and expansive in terms of the points being made. And so if you haven't yet seen episode 1 of the case for separate ancestry, please do check it out. I focus on the best lines of evidence for a literal Adam and Eve. It's comprehensive and it really expands on a lot of the points that I make in the Moments episodes. And so this is Separate Ancestry Moments 2. Moments 1 is on Patreon, and it is specific to our financial backers through our Patreon page. And so this is a full-time ministry. We're putting out full-time content, and we are in the midst of writing several more books and just putting out a lot of work for 2023. And so what we're trying to do is put more and more content through Patreon. That includes articles, videos, but also some content at least that'll be patron specific. And so for only $1 a month, as little as $1 a month, you can become a Team Standing for Truth patron, and you can receive access to a whole pile of exclusive content. So episode 1 focused on, it was about 30 minutes. Episode 1 focused on Y chromosome dissimilarity between the great apes, your humans, your chimpanzees, bonobos, gorillas, orangutans. And I covered it in great detail, went over the rescue devices that the evolutionists look to. It's just a bunch of stories, just a bunch of fairy tales, basically, because humans and chimpanzees in their Y chromosomes, which is uniparentally inherited DNA, meaning it's passed down from grandfathers to fathers to sons, male lineage specific DNA. Well, human Y chromosomes worldwide are incredibly similar. Very low genetic variation, 99.9% the same. But when we compare human Y chromosomes with the chimpanzee Y chromosome, which is supposedly our closest cousin, and we share a most recent common ancestor with the chimpanzee between 6 and 10 million years ago, when you consider overall gene content, architecture, and size differences, the Y chromosomes between humans and chimpanzees are only about 35% the same. You can see in the diagram, I actually just did an impromptu debate on this topic, among other related topics to ancestry, with several evolutionists. And so up to this point, there's been no answer to this challenge, a challenge to universal common ancestry and human evolution specifically. And so you can see in the diagram itself, the chimpanzee Y chromosome is only half the size. It's very dissimilar, only about 35% the same. And there's a break or an inconsistency in the hierarchy. And so what I mean by that is your human Y and your gorilla Y are more similar to each other in overall gene content, architecture, and size differences than the human is to the chimpanzee or the gorilla is to the chimpanzee. And that has been pointed out in these papers that it is very puzzling. It is confusing to the evolutionary community, because according to them, we share a more recent common ancestor with the chimpanzee and not the gorilla. And yet the human Y and the gorilla Y are more similar to each other than either are to the chimpanzee Y chromosome. Now, this is from a commentary article itself right here, comparing Y chromosomes of great apes. And so the authors themselves admit, because if I had $1 for every time I heard an evolutionist parrot or repeat the same talking points or untested hypotheses in these papers themselves, I'd be a rich man. Okay. And so they admit, this is 2020. Our hypothesis, and then they get into possible factors that can contribute to these massive differences. Again, that is a ton of differences. Massive gene loss, massive gene reorganization, so many changes, novel changes that involve loss in just the 6 to 10 million years since the split. And no mathematical model has been presented, only just so stories, only possible factors. And so they've admitted that, this is a hypothesis, and they suggest sperm competition, polygamous relationships within bonobo and chimpanzee groups. The original 2010 paper, I believe it was, where it talks about how divergent these Y chromosomes are between humans and chimpanzees. They suggest faster rates of gene conversion. But nonetheless, they admit it, the authors themselves, they say, we think that this situation could provide the evolutionary pressure to accelerate change on the chimpanzee and bonobo Y chromosome. But this hypothesis, which is what I've been saying for years, and they're admitting here, while consistent with our findings, needs to be evaluated in subsequent studies. So we need to see some empirical data that actually supports this idea or hypothesis, because that is a lot of change to account for. That is a massive discrepancy in the Y chromosomes of the great apes. Evolutionists would say humans are human great apes. And so rather than just saying, well, maybe sperm competition could do it. And that's why they say, well, consistent with our findings, because to them, sperm competition might be able to explain those discrepancies. But that is them just throwing something out and hoping that it sticks. And so without a sophisticated evaluation in subsequent studies, without a well thought out explanation that comprises an advanced mathematical model, that's all it is. It's a just so story. It's a maybe this or maybe that. And so that is just episode 1 in a nutshell. And so if you're an evolutionist and you're going to comment in the comment section on that portion, that was just a recap. The entire episode, for the most part, of Separate Ancestry Moments 1 focuses on Y chromosome phylogenetics, as well as Y chromosome dissimilarity. And so now we're just going to jump into the topic of episode 2 of Separate Ancestry Moments. And so with that, let's go full screen here and jump right into it. So this is from a technical paper from Nucleic Acids Research by Dr. Robert Carter. He's a biblical creationist, and he published a paper titled Mitochondrial Diversity Within Modern Human Populations. The mitochondrial genome is about 16,500 letters. To be exact here, notice the citation. The worldwide human mtDNA consensus is composed of 16,569 nucleotides. And so we've essentially discovered Eve. Okay, mitochondrial DNA, just like the Y chromosome, worldwide has incredibly low variation. There's only a few differences on average separating any two people. And as a matter of fact, we can trace all mitochondrial DNA back through one lineage. mitochondrial DNA worldwide, which is passed down on the mother's side, as compared to the Y chromosome, which is passed down on the father's side. They are both uniparentally inherited DNA. There's no recombination, okay? And this is not autosomal DNA. And there is one woman, the mother of us all, basically. And this specific paper, what it has done is it's looked at the mitochondrial DNA in the world. Dr. Rob Carter has lined mitochondrial DNA in the world up. And when you do this, what has been noticed is that 85% of the letters of the 16,000 roughly letters of mitochondrial DNA have exactly the same letter. And that tells us that Eve had that letter. And so you'll notice here, based on the current data set, 84.1% of the mitochondrial genome is invariant. Now, when we consider worldwide variability, we can see where everybody in the world has, let's say, an A, but then one person in the world has a T. Well, what letter did Eve have? Well, obviously, Eve would have therefore had an A. And so by applying this very simple system or applying this logic, we can, and Dr. Rob Carter has done so here, derive an Eve sequence, a consensus Eve sequence. Now, the evolutionary community, with no justification, would admit that, yes, this is the woman that we've essentially all originated from. This is the lucky mother somewhere in Africa 100 to 2,000 years ago that managed to spread her DNA to every single person today. That's why we have that one lineage. Okay. And therefore, they would look to this consensus sequence as being a coalesce sequence of the last mitochondrial DNA ancestor. But again, they didn't predict this. This was ad hoc, post hoc, to invoke coalescence and to essentially argue that this was a mathematical guarantee, when in fact it's not. Given what we know about how people groups and tribes historically have interbred, intermarried, and stuck within their tribes, we should, as a matter of fact, expect multiple lineages of mitochondrial DNA. Why don't we find multiple coalesced mitochondrial DNA sequences? Why only one? The Bible predicted this. The Bible claims to be the history book of the universe. The Bible in Genesis tells us that God created two first people, the first couple, our first parents, Adam and Eve. Eve, the mother of all living. Adam, the first man. And so these were Bible-based predictions, Bible-based expectations. And this data didn't have to come out to be the way it is. This didn't have to be true if evolution were true. And they did not predict this beforehand. And so this is a scientific line of evidence that meets biblical expectations or predictions. Okay. So again, by applying this logic, we can and we have derived an Eve sequence. We literally know Eve. And we know this simply because 85% of the mitochondrial genome is invariant, as we can see here in this specific excerpt from this important paper that I highly recommend reading. And most of the variation is rare. And what that means is it's only found in one people group or even one person. And because it's rare, it is a mutation that has occurred in specific people groups or a specific person. It's not part of the 85% that's invariant that basically all people have. And so what we find here is that variation is low. We know the mutation rate is fast. It's between 0.1 and 0.5 in the mitochondrial DNA per generation. And so the amount of variation to account for in the mitochondrial genome, it's trivial. And it's easily explained in just a couple hundred years. The biblical model of ancestry accounts for the low variation quite easily, because most people in the world are only a few differences removed from Eve, the Eve consensus sequence, to be exact. And then you've got your African lineages that are more divergent. Okay, so the mean or the average was right here. We can see from the paper itself, the 827 sequences within the data set contain 2,631 variant positions, and on average differed from the consensus by about 21.6. Okay, so we could say less than 30 DNA differences removed from the Eve consensus sequence. And so from Eve to getting that amount of variation, it's trivial. Okay, we're not looking to fixation. We're not assuming that coalesced sequence basically goes back further than that to previous ancestors. If that is the original sequence, the sequence of biblical Eve, and so the 21 mutations roughly diverge from Eve, it takes just a couple hundred generations to account for that. And that is also accounting for purifying selection with a mutation rate of roughly 0.1 to 0.5 per generation. And again, it's easily accounted for, low variation, a fast mutation rate, one woman of whom we've all originated from. The mitochondrial DNA is very different to the chimpanzee mitochondrial DNA. We don't have multiple lineages that would essentially be expected from the evolutionary based model. And so an easier way for people to understand how this world consensus sequence. So notice here, the world consensus sequence is unambiguous, except for a very few nucleotide positions. What it means, it's clear. It's not difficult. It's not like there are multiple conclusions that we can make. No, the amount of mitochondrial sequence divergence within humans since the most recent common ancestor, it's low. It's easy to account for. It's only a few differences. If we came out of Africa 100 to 200,000 years ago, and we understand the mutation rate is fast, and mutations add diversity because mutations are adding something that was not previously there, and people groups have spread out globally, then we should find highly divergent groups. We should find a lot more diversity. This is why the evolutionary community had to come up with the out of Africa population bottleneck, 2 or 3 of them, to account for the 1Y chromosomal lineage, the 1 major mitochondrial DNA lineage. Not to mention we have 3 major haplogroups. And after the flood, what do we have? Noah, his wife, their 3 sons, Shem, Ham, and Japheth, and their 3 wives. And so we have your major haplogroups being L, M, N, and R. And so either one of those 3 or 3 of those 4 could be Noah's 3 daughters-in-law. And maybe R is a post-Babel dispersal event. Regardless, what we see in terms of worldwide mitochondrial DNA variation, as well as the representation of it in a phylogenetic tree, as I've done in previous episodes, and for sake of time, I won't do it here, is exactly what the biblical model of ancestry would expect and would predict. Okay. And so what this is saying is it's not like it's unclear. No, the data here is pretty clear. And so we know for the most part Eve's sequence. And since the mitochondrial DNA, it is a small chromosome. It's a tiny part of the genome. People who've taken biology and genetics classes understand it's the powerhouses of the cell, essentially. It's roughly 16,000 letters, 16,500. And it's only transmitted through the woman, from grandmother to mother to daughter. Okay, so every time a mutation is added per generation, mistakes occur every single generation, right? We have DNA repair enzymes in our genomes, but they don't work perfectly. And so mutations accumulate, and every time a mutation's passed on, a new branch in the family tree is formed. And so you could take those branches and you can essentially back them up right to Eve, or you can start with Eve, the biblical Eve. Eve has kids, and Eve's kids have kids, and branches are formed, mutations are inherited. And all of this is accounted for in just 4,000 to 6,000 years. It's amazing. And the fact that all women today have nearly identical mtDNA sequences to the woman of whom we've all descended from, that we have the Eve consensus sequence. I've debated this numerous times in formal debates. There's no good response to the data that we have here. Genetics, guys, is the best way to determine ancestry, because it's in our genetics that we can best answer this question of ancestry, since it's genes, traits, and genetics that are inherited sperm and egg. It is a direct way to answer this controversy: universal or separate ancestry. A bone found in the dirt, a fossil, that's not inherited sperm and egg. Geography is not inherited sperm and egg. Geology is not inherited sperm and egg. Genes and traits are. And so through this direct means to answer this question of ancestry, we can see just how powerful the evidence is for separate ancestry. This is exactly what the biblical model would expect. We've identified the Eve sequence, as you can see here. It's been published in the secular literature by young earth creationists. Now, this paper here, as you can see, in 2007, mitochondrial diversity within modern populations. As I've pointed out, Dr. Rob Carter, the author of this paper, he took a database of mitochondrial chromosomes around the world. He aligned them all. And by doing so, he was able to discover where the mutations were through this process. And that's how we find a consensus sequence. So earlier, I talked about how you can look to, your invariable positions or your variable positions. But a better illustration for people would be, and I've used this in the past. So let's say if I handed out a document, a manuscript of some kind, to 100 different people, and I asked them to copy it manually. What we would actually find, therefore, is mistakes in every copy written out by each person. Every time a person writes out a copy, a mistake or two will be added. And so with this, we can go through the copies. We can find the rare deviants, as Dr. Carter has done here with mitochondrial DNA worldwide. He's looked for the rare deviants, the mutations, the differences. He's looked to the invariant spots within the genome, and he's been able to derive this consensus sequence. Okay, so you find the rare deviants, let's say in our illustration, in the copies of these manuscripts, these 100 manuscripts. Well, by removing them, you can now come to that original manuscript or copy. In this paper, again, I want to reiterate the fact, Dr. Rob Carter discovered roughly 21 mitochondrial DNA mutations per person removed from Eve. That doesn't mean that, if I have 21 mutations removed and, somebody else does, it doesn't mean that it's in the exact spots. It's just roughly 21 mutations or deviations removed from the Eve consensus sequence. We also know that the rate of mitochondrial DNA mutations is variable within people. It's approximately 0.1 to 0.5 per generation. And that's very high considering how small the mitochondrial DNA compartment is. The Y chromosome is a lot larger than your mitochondrial genome. And the mutation rate is about 3 per generation. But both compartments have very low variation. And so right here, a couple papers, pedigree-based mutation rates, 10-fold higher than phylogenetically derived rates. Now, what the evolutionists will look to is the African lineages, where they diverge more from the mean, where you're looking at, between 120 mutations removed. So it's on the higher end. And they'll argue that Africa, having the most diversity, and since everything nests within Africa, Africans must be older than non-Africans. And to them, this refutes the out of Babel model. To them, this demonstrates an out of Africa dispersal that would have occurred way further back in time than 4,000 to 6,000 years. But what the evolutionary community doesn't realize is that in terms of the nesting, everything is going to nest within the epicenter of genetic diversity. That is a side effect of where, firstly, they would pick a root on a phylogenetic tree in your deepest branches, or your deepest lineages in Africa, since they're assuming that your deepest lineages, your largest branches, which is a reflection of DNA differences or mutations over time, they have the most diversity, and therefore Africans are an older population, is basically what they would argue. But again, the nesting pattern is a side effect of their rooting, of that assumption, and everything is going to nest within the epicenter from which we've all originally dispersed from. And the Middle East and Africa are very close to each other. And so where we actually place the epicenter of genetic diversity, or where we've all originated from and have dispersed from, is based on numerous assumptions. I've had a number of debates on this specific topic. And so many of those assumptions for the evolutionists, unfortunately for them, are unknowable, unprovable. And so realistically, for us as biblical creationists, all we need, and the things that we need, are supported and backed up by the scientific literature. All we need is higher mutation rates in your deepest lineages, selective sweeps, for example, where let's say there was a selective sweep across Eurasia that resulted in your older lineages being completely wiped out, with older lineages in Africa remaining or surviving. Africa could have had, a higher initial population size with more working PRDM9 genes. Recombination, for example, is carried out, I got papers on this, is carried out through a gene, the PRDM9 gene, where basically it looks for a certain set of letters on the chromosome, finds it, grabs onto it, recombines. And it turns out that Africans have more of these sites than non-Africans. Okay, so more people could have come into Africa with more working PRDM9 genes, or, your early biblical patriarchs, at least in terms of the Y chromosome, could have been passing on more mutations because they're living longer. And so people are being hit, generations are being hit with a whole bunch of new mutations. Another big thing to consider is mutations in important DNA repair enzymes, because we understand that environment can significantly affect mutation rates. Okay, notice here, 2022, environmental exposures in parents, such as ionizing radiation, can influence the number of mutations transmitted to offspring. In this study here, 2 families had 7 times more mutations. They passed on 7 times more mutations, I believe it is. And so this is real-time evidence that of hypermutation. And notice this, with fathers carrying damaging genetic variation in DNA repair genes. So all of these factors that we have to consider, including the fact that mutation rates are variable, recombination rates are not constant. Now, recombination is obviously going to apply more to the autosomal DNA, of course, not uniparentally inherited DNA, but nonetheless, it's still something to consider. And so if you have 2 groups of people, and one is closer to the equator, Africa, right, is closest to the equator, and there's excess radiation, environmental triggers. And so we understand environment and stress can damage DNA repair enzymes. And in starvation conditions as well, the body is worried about tomorrow. It's not worried about getting cancer 50 years from now. It needs to survive till tomorrow. And so DNA repair enzymes, unfortunately, might be broken down. That means more mutations are going to be passed on. So if you have 2 lines and you have one line that doesn't have broken DNA repair enzymes, but you have another line that does, as that line diverges from this line is going to pick up more mutations than the other line. And so it's impossible to have this nice and neat organized tree where we can pick a root when you have 2 groups existing at the same amount of time and experiencing different environments, different stressors, different conditions. They exist in different places geographically. But one line is accumulating more mutations than the other. That means one line is going to have more diversity than the other. And so when evolutionists look to that as being representative of time, they're wrong, because faster mutation rates can drive genetic landscapes. Faster recombination rates through the PRDM9 DNA element can drive genetic landscapes. Selective sweeps can drive genetic landscapes. There are a number of things that we have to consider that drive genetic landscapes. What about people groups or lineages in colder areas around the globe? Let's say colder spots in Europe versus Africa. Well, natural selection might act differently in colder regions than in hotter regions. And so more mutations might accumulate in one region versus the other because selection's stronger in one. Let's say selection's stronger in your colder regions that are outside of Africa. And so you have maybe the same amount of mutations accumulating, one could say, but selection's stronger in one. And so those mutants are removed from the equation. Okay, these are just a number of factors that I've talked about in great detail, and they are all factors that are real. So again, two families had genetic drivers of germline hypermutation, with fathers carrying damaging genetic variation in what? DNA repair genes. So this is today, we understand that closer to the flood, the effects of the flood are what? Heat, radiation, you might have had excess uranium and other, damaging environmental triggers, factors in rocks, in waters, in mineral, things like that, that your early post-flood people are affected by. Your Neanderthal group, for example, they go into a certain part of the globe where they're isolated, they're inbred, and there's just a lot of factors at play. Okay, notice here, environmental exposures influence the number of mutations transmitted to offspring. And so it's difficult, especially early in history after the flood, to look at a branch and assume that that's an indicator of time, when in fact a whole bunch of mutations could be passed on per generation. Notice this. We also found the overall point mutation rate is significantly higher in Africans than in Europeans in this specific region. And I'll tell you, that's not the only region in the genome that's experiencing more mutations. Our findings imply that defects in DNA repair genes can increase germline mutation with a shift in environment and the rekindling of culture, stress, conquest, war, disease. Just again, the shifts in environment, the drastic shifts in environment post-flood would undoubtedly result in what we're seeing here, damage to these important DNA repair genes. And so just the generation after generation could be just getting slammed with all of these new mutations. Okay. And so out of Babel, all you really need is waves and waves of people moving into Africa from Babel, which makes sense, where Africa is located and where the Middle East is located. And so many of Noah's descendants could have moved into Africa. And as a result, they're bringing in what? More and more diversity. And so Africa is starting with more diversity. And so your epicenter of genetic diversity then, being the Middle East and Africa regions, you're going to have that same nesting pattern. It's a side effect of where we position the epicenter of genetic diversity, basically. Okay, so you have waves and waves of people out of Babel moving into Africa. And then within Africa, you have people spreading out and then existing in tribes. And within those specific tribes, they're intermarrying, interbreeding, obviously. And so each tribe is diverging from each other because more mutations are accumulating, different mutations are accumulating. And so each group is moving from each other. That's why even with diversity within Africa is more than all of outside of Africa. And so Africa has had a very interesting history. Okay, we also understand that in small populations, mutations accumulate faster and they're fixed faster. And so we have rapid fixation of new mutations. which means populations are going to diverge. They're going to be more and more different. Okay, so the last thing I want to cover in this specific video, it's kind of branching off from episode 1 of both the case for separate ancestry and also uh, and separate ancestry moments. Okay, so right here I want to cover, which I've covered in great detail in the previous episodes, but I want to go over a couple more aspects of this specific tree and just how interesting it is in terms of what we can derive from history. Okay, so again, this is a tree made by Dr. Rob Carter, who's put a lot of work into this, a lot of time into this, and it's comparing 10 million letters in the Y chromosomes of a couple hundred men. Now, this tree comprises the signal, just like the mitochondrial DNA tree. Right here. It comprises the signal of an exponentially growing population, which we understand from the Bible. We have Adam and Eve, and then from Adam and Eve, it's a single generation bottleneck that's followed up by rapid and exponential population growth. After the flood, we have 8 people, 3 reproducing couples, rapid and exponential population growth, but that population grows and remains in the same spot until they spread out. God confuses the languages, and then people spread out worldwide, and that's where we can get into allele frequencies. That's where we can get into these geographically specific Y chromosomes, African Y chromosomes, European Y chromosomes, okay, Chinese Y chromosomes. That is because as people spread out, led by the men, led by the Y chromosomes, as per the Bible, each specific group, as they spread out, they begin to independently accumulate their own mutations, their own unique genetic markers. And so we now have these geographically specific Y chromosomes. And yet, when we compare all the groups, we compare Y chromosome variation worldwide, it's all low. It's all nearly identical. But if out of Africa is true and people spread out and they start accumulating and acquiring their own mutations, we'd expect some highly divergent Y chromosome groups. We'd expect a lot more variation and diversity in this uniparentally inherited DNA compartment, and we do not find that. And that is a major inconsistency with the evolutionary model when compared to the out of Babel dispersal. So this tree, it comprises the signal of an exponentially growing population. The center of the explosion, okay, is our last Y chromosomal ancestor, Noah. He's in the middle of all these people. Where exactly, we don't necessarily know, because rooting the tree is difficult since there's so many factors at play. And so an unrooted tree like this gives us a natural representation of the data, and we can still look at this tree and we can see history. Okay, for example, look at the R1b, and this is where I've got this one because it's a little bit more detailed, okay? So you can find this tree from these specific papers. And then you can also find this tree, which is a little bit more detailed from this specific article. So if you actually look at the R1b on this tree, okay, this group is actually 80% of Western European men. Western European men. And most European men carry this group, okay? R1b. Now, R1a, we find is... One second here. Okay. So R1a we find in Pakistan and Africa, or Pakistan and India, I'm sorry. And Q is Native Americans, which is right here. Okay. O is common in Japan. It's common in Europe, or in China. Okay, we've also got E1B1A, which comprises 95% of African men. But E1B1A actually branches off of what? Well, you've got this broomstick. This is a broomstick model, okay? Where you've got living people. The branches are mutations. You can count up the mutations. They go back to a common ancestor. Okay, but you'll notice that your E1B1A branches off of E1B1B. having a hard time keeping this mouse in view because I want you guys to see. Okay, so again, let's try this again. E1B1A branches off from E1B1B, which is non-African. D is non-African, and C is non-African. This means, to be specific, African branches off of what? Non-Africans. And so this would tell us that it most likely, and we could make all sorts of conclusions and inferences based on this tree, but this one specific observation tells us that it likely arose outside of Africa, and then they invaded and took over. Okay, so there's some very interesting history on this tree. And again, when it comes to the Y chromosome, when it comes to the mitochondrial DNA, when it comes to the DNA in general, we have some amazing evidence for a single dispersal of people across the planet that originated from a location very close to the Middle East. And so those basic assumptions in terms of where we're going to place that epicenter of genetic diversity, where we would root the tree, where we would assume we've all originated from, you're going to get that same side effect, basically, the nesting pattern that evolutionists argue is, in their mind, irrefutable evidence for the out of Africa theory. But as we've demonstrated in this shorter video, that is not the case. So guys, it is a great time to be a biblical creationist. We know Eve, and the Eve consensus sequence, it is published in the secular literature, and the evolutionists have no good response to this data. And so with that, guys, I want to recommend everybody share this content around, get caught up on this series as well, because as I work through the case for separate ancestry and move on to future episodes, the next episode I'm working on for that, the longer series, has to do with genetic entropy. But also, as I continue doing these moments, which I guess one could say they're longer moments than you'd think, but trying to keep them between 30 and 45 minutes, we are going to be touching on some fascinating data. So with that, guys, God bless.